probabilistic flavor, also some discrepancy theory. And then we'll have the open problem session again. So our first talk is Octavio Arizmendi, and he'll tell us about finite free cumulants.
Thank you very much, Nikhil, for the invitation. So I will talk about cumulants, which is like the combinatorial approach to free probability. But let me first use some slides to give some introduction to free probability. I suppose that I see here some experts around. You know, free probability was embedded here. So, what is the framework? The framework is, instead of looking for sigma algebras, we have algebras, and instead of having expectation, we have general linear functional. So here, we care more about the random variables, which will be elements in my algebra, and we have a linear functional which sends the unit in the algebra to 1. And this is just to make it a probability measure. So we will typically have some further structure, meaning that we will have an adjoint, and we will talk about positivity, meaning that that will be positive if it can be written as A star A, and the functional will be positive if it sends positive things to positive numbers. The idea is that we want to think this as the conjugate, the transpose conjugate of a matrix. Okay, and what is the typical algebras that we work with? Because we want some topology, well, we will work basically with C-star algebras, which are just bounded operators, most almost. Okay. So in this framework, we can talk about the moments of a random variable. So the idea is that we get information of my random variable through how the linear functional acts on powers. And this is what we call the moments of a random variable, just like expectation of x to the k is the usual moments. And this is how we can associate a measure to a random variable. Well, we just say a measure, the distribution of my measure of my random variable is the unique measure whose moments are the moments of my random variable. Of course, this in the general framework may not be unique, but if we are in a C-star algebra and A is bounded, then we can be sure that, and this is self-adjoint, we can be sure that actually there is a real measure which satisfies this identity. Okay, and here this is what I mean, that if you want probabilities here, when we put k equals 0, we want this to integrate 1. That's why we assume that phi of 1 goes to 1. Okay, so and all these ideas come from, this framework comes from quantum mechanics basically, where this functional here is just the vacuum vector. Okay, so typical examples, of course, we want to generalize classical probability. And here I should emphasize that we are losing information because we don't have realizations. Okay, meaning we don't have events. We're just looking on distributions and random variables, not really on events. So this generalizes in some sense, but not in the general sense that we can get probabilities from this. Okay. Another important framework is for this talk is matrices, n by n matrices, and here the functional that typically we use, but this is not the unique one, is the normalized trace, and I use normalized so that we have the identity goes to 1. And of course, I can combine these two, and I get random matrices. And here, the usual linear functional that I consider is combining these two, meaning I take trace of the expectation, or expectation of the trace, whatever you want to see. And this, of course, also satisfies the property that 1 is sent to 1. Here, the unity is the same unity as for the matrices. Okay, and what are the distributions? Of course, the usual distribution in probability is the distribution in the way I defined. For matrices, this is just the so-called spectral distribution or eigenvalue distribution. So this is a distribution which puts mass 1 over n to each of the eigenvalues when the matrix is, say, normal or self-edge. And for random matrices, we don't get a random eigenvalue distribution, but we average over all of them. Okay? So this is not a random object. This is, for a random matrices, this is a fixed object, which is the so-called average eigenvalue distribution. And typically in application, one studies this distribution and then uses concentration of measure to show that actually the random eigenvalue distribution is very close to the average. Maybe another more algebraic example, and somehow where free probability came in the picture, comes from the group algebra. So I have the group algebra, which is just finite sums of elements in the algebra with complex coefficients, say. And the linear functional tells me what is the coefficient of the identity in the group. Yeah, so I have here a sum, and I just care about what is this coefficient for E. Okay, and of course, you will think that this doesn't give me a lot of information, but if I consider powers of this element, then somehow I will be able to recover most of the information of the coefficients that I'm looking at. Of course, it depends on the group. But okay, and the important observation is that if I have two groups and I consider the group generated by words on G1 and G2, so I mean they are the free group generated by G1 and G2, then the linear functional satisfies this property that for any element in the group algebra that has coefficient 0 on the identity, and for any families that satisfy this, then if I make the product when these A's are in G1 and these B's are in G2, then because there is no relation, there is no way that I can get a coefficient in the identity. Okay, and this is somehow, this observation says is that if I take alternating products of elements which are in different, which have mean 0, then the product will also have say mean 0. Okay, and this motivates the definition of Voiculescu. And what this is telling us is that if we have algebras which somehow have no relation between them, then this should be captured by the linear functional in this way. And in fact, this is an if and only if for the group. So two groups are in free position if and only, algebraically if and only if they satisfy this relation with respect to the functional that I defined. Okay, and okay, for two random variables, we say that they are free if the algebras are in free relation. And just to mention, there are many development of this theory, like central limit theorem, infinite divisibility, stable laws, Levy processes, even entropy. So many analog things. Okay. And maybe for this talk, the first important result is, of course, the central limit theorem. And there is a big difference here is that, of course, we normalize and we don't assume that they are classically independent, but free independent. Then we get the semicircle distribution, okay, which is bounded. So it's very different from Gaussian. Okay. And in fact, there is improvement of this theorem. One of them is a result by Berkovich and Voiculescu, where they actually show that for large n, this sum is absolutely continuous. The densities converge uniformly to the density of the semicircle, and also the support, provided that the original measure was bounded, the support goes to the support of the semicircle distribution. Which is, of course, not the case, say 2 is not the case in the classical central limit theory. But this is a very strong way, which is called superconvergence. Okay, and another result, this is analog to the classical case, is that we also have a very Esseen bounds, meaning that the distance of this sum, normalized sum, with the semicircle distribution can be bounded by some numbers which depend on, say, the fourth moment, and they are of order 1 over square root of n. Let me just mention that in this context, maybe it's important that the example of free product of graphs. Okay, so the free product of graphs is here. Let me just put an example. We start with rooted graphs. Here I chose lines, and then I put one graph, and then in each vertex I put the other graph, and then in each vertex I put the other graph. And here I wanted to emphasize that if I consider these copies of my graph embedded in the free product, actually these guys are in free relation. Meaning it's not only that the distribution is the free convolution, but actually that as operators with respect to the vacuum vector, they are free or free independent. Maybe another example is this one. And I just want to mention that as it was observed yesterday, of course, there are no new cycles. And this is very different from Cartesian products where actually lines with line gives the grid, which make a lot of cycles. And also maybe the example that is important is, of course, the irregular graph, which comes from taking n free Cartesian free product of the K2 with itself. Okay, and a direct consequence or corollary is, of course, the central limit theorem for the free product of graphs, which says that this converges to the semicircle, not properly normalized. This is just rephrasing the classical central, the free central limit theorems. Okay. So now I will talk about what is a free cumulants. So free cumulants were introduced by Voiculescu, say analytically, and then revisited by Speicher in the combinatorial way. Okay, so to calculate free convolution, so we need the so-called Cauchy transform, which is just the expectation of the resolvent. And then the R-transform is just given by the compositional inverse of the Cauchy transform minus and taking one pole in 0. Okay, and the way that we can analytically calculate free convolution is just by adding the R-transforms. So this is the analog of the logarithm of the Fourier transform in classical probability. And okay, there is something similar for the free convolution, which is called for the multiplicative free convolution, which is called the S-transform. And what we want is to have the thing is, if we have actually the moments are calculated by the Cauchy transform, somehow if we want to calculate the moments of the free convolution, the formula becomes very complicated. So we want numbers which have the same information as the numbers that have the same information as the moments, but that somehow behave nicely with respect to addition of random variables. Okay, so we will have three properties. The first property is somehow saying that they have the same information, meaning that if I know the first n moments, I know the first n cumulant and vice versa. The second property is that it behaves well when I multiply by a constant. And the third one, and probably the most important one, is that if I have independent random variables, say freely independent or classically independent or n independence, then they should be additive. Okay? And with these three properties, actually I can prove a central limit theorem for any notion of independence that I have, provided that my random variables have all moments. And the proof is very, very simple. Okay, so consider just a normalized sum of random variables. Here it should be this is a mistake. Okay, and let's calculate the first cumulants just to. So the first cumulant, so the central limit theorem assumes that first cumulant is 0 and second cumulant is 1, just to normalize. Okay, then the cumulant of the sum of these random variables normalized, so this guy goes away by n to the 1/2, and then I add all cumulants which are 1 because they have the same distribution as A. Okay, so this is 0. Then I go for n equals 2, and then this n to the 1/2 goes as 1/n. And then since these are identically distributed, these are just n times k2. And then they cancel and I get 1. Of course, but this is what it should be because I normalize so that the variance and the mean stay fixed. Okay, but then if I go for n larger than 2, what will happen is that I will have the same phenomena, but instead of getting this 1/n, I will get 1/n to the n/2. And as soon as n is bigger than 3, then this goes to 0. So what this is proving is that the limiting distribution should have cumulants 0, 1, 0, 1, 0, 0, 0, 0. For any notion of independence, and this proof, of course, also was for classical central limit theorem, provided that I have all moments. Okay. Okay. So the definition of free cumulants is, of course, we want that this is additive with respect to free convolution, so it should be related to the R-transform. Since the R-transform is additive with respect to free convolution, then if I take the coefficients of the series expansion, say, when I have all moments, then this satisfies the desired properties. The fact that it satisfies the other properties is not so complicated also. But maybe I want to emphasize the combinatorial approach to free convolution, to free convolution, and is given by the so-called moment cumulant formula. Okay, so this is, I should explain a little bit on what do I mean by these two things. So by a non-crossing partition of size n, I mean I divide the subset 1 to n in subsets such that if I draw them in the circle, they do not cross. Okay, so a crossing partition will be, say, so this is a crossing partition. This is what we don't want. Okay, and then if I have a partition sigma, here it's the partition 1, 2, 3, 4, 6, and 7, 5. Then a free cumulant will be just the product of the sizes of the blocks. In this case, it will be R3 times R2 squared. So this is what this formula is telling me, is that if I want to recover the cumulants from the moments from the cumulants, I just sum over all non-crossing partitions of size n, and then I do this multiplicative multiplication of the sizes of the blocks. Okay, so for instance, M1 is just R1, M2 is R1 plus R2 plus R1 squared, and so on. So there is also a multivariate version of cumulants, which is just given by the same formula, and the difference is the property of additivity of cumulants for one-dimensional cumulants is generalized to the vanishing of mixed cumulant. Okay, so this should be R. So, and this formula, what I'm saying here is that in particular, if I have only A's, this is saying that since the mix, if I take Kn of A plus B by the multilinearity of the cumulants, then I will have this relation. So this is more general than the previous one. Okay. So finally, what is the relation between random matrices and free probability? So we say that two families, or let's say two pairs of random variables in some non-commutative probability spaces converge in joint distribution to a pair if actually the moments or the joint moments convert to the joint moments of the limiting distribution. Okay, and in particular, if these A and B are free, we said that these pairs converge, so are asymptotically free. Okay, and the main example comes from, of course, random matrices. First noticed by Voculescu is that if one takes two Gaussian independent matrices, then as n goes to infinity, these two are asymptotically free with respect to the expected trace. And then one can prove that this holds almost surely. And another also important example is when one takes A and B, say deterministic matrices, meaning there is no randomness, and then I conjugate randomly with the Haar measure on the unitaries, and of course this will have the same distribution as n, but now they will be somehow in free position. Okay, and the intuition is that when n is large and the matrices are in random position, somehow I lose any relation. And this has been used to actually predict the shape of matrices that we can translate to calculations in free probability. For example, here the anticommutator. And maybe for this conference, it is important, or an important example was that doesn't follow from the previous one, is when I consider permutations. So if I have two random permutations, they are actually asymptotically free. And this explains somehow why the Kesten-McKay laws appear in McKay's result, just because the random regular graphs somehow can be thought as the sum of n random permutations. And in fact, the free convolution of K2 with itself gives this so-called Kesten-McKay law. Okay, I will just remind the basics about finite free convolution. I will go fast because I guess in this conference everybody knows what finite free convolution is. So as I mentioned before, if I have A and B which are deterministic, and then I conjugate, what we typically used to do is to consider the moments and then average, take the average of the moments, and then what I get is the eigenvalue, average eigenvalue distribution of the sum. Okay, and the new approach is not to look at the distribution, but look at the characteristic polynomial. So what I'm doing is just take exactly the same framework, but instead of taking the expected moments, I take, say, the expected coefficients of the polynomial, okay, which surprisingly gives another polynomial which is real rooted. Okay, and this is one of the main results of MSS. Okay, and this is exactly what I'm saying here. And of course, if this wants to be a definition, one should see that this doesn't depend on A and B just as free convolution. Okay, actually, there is an explicit formula for the coefficients of the finite free convolution, and this was already studied by Walsh and others long time ago. Okay, so somehow what we're saying is that if I have these coefficients, and these coefficients I go to this somehow convolution formula for the coefficients. Okay, and here these factorials actually play a big role in the calculations. For the finite free multiplicative convolution, there's a similar one. And maybe one of the applications of this, or why it was called finite free convolution, is that if one looks at the R-transform, instead of having an equality, we have an inequality. And this was used to bound the roots of the finite free convolution of P with itself. Okay, and maybe for a free probabilist, I will be more interested in the fact that proved by Marcus that when d goes to infinity, actually this inequality is getting tighter and tighter, and I get somehow free convolution. Okay, so what I want somehow to understand is which properties from free probability already appear in finite free convolution. And in fact, maybe it can happen that the new properties that we didn't know in free probability can emerge from properties that are discovered in finite free convolution. Okay. So, and then since I come from this finite free cumulant approach, then the first question I ask myself is, are there cumulants for this free convolution, for this finite free convolution? And the properties that I mentioned before can be easily rephrased. Of course, the first one is that the cumulants should be somehow polynomial in the first moments. Second is homogeneity. And here I need to know what does multiplying by a constant means. And the third one is exactly the same. So here, just for one, I replace by 1 prime, and here I put this not a monic polynomial, but a polynomial with this coefficient in the leading term. This is just for convenience, just because the calculations are simpler.
What's d?
D is the dimension of the polynomial, so it's the degree. Sorry, the degree of the polynomial, so the dimension of the matrix. And what this means is that so what is d lambda of a polynomial is just that I spread the polynomials by multiplying by lambda. So this means x, evaluating x over lambda. And of course, the last one is the most important and is the same one. Okay, so there are, let's say, two definitions of finite free cumulants. The first one comes from the R-transform defined by Marcus, which was defined in this way, but I liked more in this way. And one can easily prove that this linearizes finite free convolution. And observe here that I have a mod C S to the D, meaning I chop this series. Okay, and this is just because in finite free convolution, what we're doing is almost like a multiplication of polynomials, but I'm chopping the last terms of my polynomial. Okay, and so if I will start with this theory, then say the definition will be, of course, the series will be additive, and then I will need to take the coefficients of my series. Okay, and maybe the first theorem, or the definition with partitions looks as follows. Let me just try to explain a little bit this formula. Okay, so what I want is a formula that involves partitions and cumulants and then some coefficient, which here is somehow complicated, and I will explain more about this polynomial and how it behaves. Okay, and the way one proves this is in two somehow simple steps. One is first I go from moments to coefficients, and then I go from coefficients to cumulants. Okay, so the two formulas so where does these formulas come from? It comes from this first formula, which is, so this is known, so how to get from a polynomial coefficients to the moments. This is just changing basis for the symmetric functions. Okay, so this is basically Newton's identities.
Can you say what like mu, 0, pi is?
Sorry. This is the Mobius function in the partitions.
So it's a totally different mu.
Totally different mu. This is just, sorry, so if you have this formula and want to go from this formula to this formula, so there's an inversion formula in general if you have a partition, sum over partitions, and this is exactly mu. Okay. And we have also a coefficient to cumulant formula, and then if I combine them, I get what I want. Okay, and I can prove easily with a.
Can you go back to the previous one just to see what n factorial pi is?
N factorial pi is just the product of the sizes of the block factorial.
And the d parenthesis pi is
D parenthesis phi is so D
like the descending factorial?
the descending factorial, Pockhammer descending factorial, and then I evaluate as in that way. Okay. Yeah. Okay. So using this formula, one can prove that cumulants, finite free cumulants, are additive without relying on Marcus result directly. And let me just analyze a little bit how this formula looks like. So first of all, you see when d goes to infinity, one wants to recover free cumulants. And from this formula, it's not clear at all, because somehow if d goes to infinity, somehow you want to see that here you have a d to the n plus 1. Okay? But in this formula, in fact, d to the n, so in this polynomial, d to the n appears in principle. So it is not trivial at all that this polynomial is of the right order and that the coefficients are correct. So this is a lemma that, in fact, and the other thing is that we don't, here there's a typo, we don't have, in the free cumulant formula, we have partitions which do not cross, but we have here partitions, all partitions. So we need to take care of these two things. Okay, and maybe the hard calculation or proposition was actually to prove that this is true. And our proof is not very nice. We use induction on n. And in fact, having a combinatorial proof of this will be very nice. Okay, so proving that this polynomial is of degree n plus 1 minus sigma, and that the leading coefficient is this one. Okay. So assuming this proposition, then why do finite free cumulants approach free cumulants? So the reason is, in fact, that with this proposition tells me that I can write moments in terms of cumulants first in summing over partitions, and then how do I change from summing over partitions to summing over non-crossing partitions? Well, for each partition, I need to multiply by the number of non-crossing partitions of certain type, and divide by the number of partitions of this type. And this is actually exactly this coefficient. So this coefficient is not arbitrary. This has an interpretation, which is exactly what I'm saying. The number of partitions of certain type, meaning with a fixed block structure, divided by the analog of the partitions. Okay. And as you see, here I want to mention that typically, for example, in random matrices, when Catalan numbers appear, typically we have like two types of partitions, one that go to 0 in the large n limit, and the other ones that go to 1. Here it's not the case. So this kind of asymptotic behavior, I don't think this was observed before. What I want to say is that the reason why finite free cumulants approach free cumulants is very different than the reason, for example, that random matrices are asymptotically free, at least combinatorially.
Is there a bijection between the non-crossing partitions and crossing partitions? That's what you're asking. Like, is there a bijective proof of this? Like, is there some mapping between non-crossing partitions and regular partitions?
You mean not a mapping that is like
that gets that?
Gets that to that? I don't think so. This is the point. Like, this is just a coefficient that appears in the leading term. Okay. And then the proof is just using exactly this fact that I'm telling. Okay. And as I mentioned before, we don't have a very nice combinatorial proof of the fact that this polynomial. We have other ways to write this polynomial. For example, here is sum over partitions which join is the total partition d to the number of blocks of, say, rho, and here the Mobius function of 0 rho. And we have maybe, I don't know if this is a nicer formula or worse formula for the moment cumulant formula. Combinatorial, but somehow it's as hard to handle as the previous one. Okay. So maybe you just finish with some applications and examples. So why are cumulants useful?
That's a quick question. Do you have finite mixed cumulants?
There's no finite mixed cumulants because there's no finite free independence for the moment. Right? So actually having finite free convolution and finite free multiplicative convolution at the same time seems to be a hard thing. Yeah, so it's only very specific examples satisfy this. So the notion of independence should be first on the table, and then we can talk about mixed finite. Of course, one can try to use these cumulants as and just assume that mixed cumulants vanish, but I don't think this is the correct answer. Okay, so of course one can prove a central limit theorem just as the way we did for the free central limit theorem, and what we get is just a polynomial whose cumulants are 0, 1, and then 0, 0, 0. Okay, and then one applies the moment cumulant formula, and what one gets is exactly that. In fact, one uses the cumulant coefficient formula better, and one can get actually what are the coefficients of my polynomial explicitly. And this is, as Marcus proved before, this is just the Hermite polynomial. One can also ask what is the analog of the Poisson distribution. So the Poisson distribution is the measure who has cumulants all lambda. And here one can actually calculate what is the polynomial. However, it is not true that for all lambda, this is a polynomial with real roots. So this means that the Poisson is not infinitely divisible, as in the free case and in the classical case. But other things are in accordance with free probability. For example, that the atom of the Poisson lambda is exactly the same as in the free probability. Okay, so this is one question. Is we saw that the Poisson doesn't satisfy what it should be, which is infinite divisibility. So one can ask about infinite divisibility in finite free convolution, and the answer is somehow disappointing, because the only infinitely divisible polynomial with respect to finite free convolution is actually the one coming from central limit theorem. And after some reflection, what happens is that you cannot make many infinitesimal limits. So how one gets, for example, the Poisson distribution? The Poisson distribution is the limit of the law of small numbers. But we cannot make this kind of law in finite free convolution, because polynomials do have at least 1 over d in each atom. Okay, for a law of small numbers, we will need like 1 over n for n very large. Okay, so this is a little bit disappointing, but this is what it is. But another property that is true for in free convolution, which is not true in classical convolution, is that in fact I can talk about mu t, meaning mu to the power t, for all t bigger than 1. So this is the polynomial whose cumulants are t times the original polynomial. Okay, and while this is not true, that one can talk about t bigger than 1, there is some t such that the polynomial to the power t is not only real rooted, but also has different roots. So this is somehow similar to free probability, but let me just point out that t is not 1. We know this. We can give a bound on how large is t. So how small is t, but this depends on d, and this goes to infinity when this goes to infinity. So this doesn't prove actually the free version. And in fact, the proof of Nika and Speicher really cannot be translated here, because it relies on some relation between free multiplicative convolution and additive convolution. In fact, free multiplicative convolution with projection. But here this doesn't hold. But we use more the approach of Bercovici and Voiculescu, which is actually the same paper as the one where they prove superconvergence. And in fact, what they studied is somehow which functions are R-transforms of a measure. We can also do a Esseen theorem, meaning what is the distance between the n convolution to the central limit theorem. And here the rate of convergence is the same, but here the constants are terrible. Also it depends on d, and it's very large. And maybe just to finish is that another thing that holds for finite free probability that doesn't hold for classical probability but holds for free probability is this called failure of Cramer's theorem. Meaning that in classical probability, if two measures add up a Gaussian distribution, then both of them should be Gaussian. And this is not true also for finite free convolution. Okay. And let me just mention that all these proofs, provided that we have cumulants, are much easier in the finite free version than in the free version. They're just like one-line proof. Here maybe we need some estimates, but it's not really deep, the mathematics that are needed for this theorem. So I'm really hoping that finite free probability gives a lot of insight in free probability. For example, in yesterday's talk, they were talking about L meshes. Okay, how does this translate to free probability? Well, this translates in the fact that if we have that we can bound the density of the free convolution in terms of the density of the convolved measures.
So, but in this proposition, the constant goes to infinity as d goes to infinity, right? So
Yes.
you can't get the.
I cannot get that. We should be more precise on our
Is it
bounds.
possible that you could get a constant that doesn't depend on d? Or
I guess yes, but we will need to work harder. The thing is that here actually the proof is very simple somehow. We didn't work out. The thing is that basically what these constants are large because getting from cumulants to moments and vice versa, somehow it's for the moment very complicated. So we have positive and negative coefficients which we are not able to grasp very well. So this is the reason. But I do believe there is a constant, which is general.
Can you form like a non-IID version of the Esseen result where like, you take the finite free convolution of n different polynomials? Maybe the bounds will depend a little bit on.
Yeah, as long as you see here is exactly what it's telling you, at least for this proof. This is as long as you can bound the max of the cumulants in some way. This would be
are the bounds much worse than the non-IID variance?
Well, they have to have some dependence on like how different the distributions are. But I mean, I don't know, there's type bounds that recover the type bound in the case where they're all the same.
So in fact, let me just, so in fact here somehow the idea of the proof of variation is the following, like if you have finite variance and then the other moments cannot be so large because you only have d roots. Right? You cannot have many points very, very far because finite variance, set variance is 1. Okay? So at the end, you can bound where the roots are, and this can help you bound all of these guys. So somehow, I don't think the proof will be very different. I think it should be very similar. Okay, let me just say thanks, and we can do for more questions.
Any questions? Okay, well, let's thank Octavio.